Talking about chapter 8, we get to talk about gases. And this is really cool because if you guys are going into respiratory therapy, or if you've ever had asthma, have friends that have asthma, we actually get to see like the barometers and what the different gas concentrations mean and how they're measured. So respiratory therapists assess and treat a range of patients. They perform a variety of different diagnostic testing, including measuring the breathing capacity and the concentrations of oxygen and carbon dioxide in the patient's blood, as well as in the pH of the blood. Generally, molecules with fewer than 5 atoms in the first 2 periods of the periodic table are gases at room temperature. So these guys, right? And the following are also gases. So hydrogen, nitrogen, oxygen, chlorine, and fluorine. So they're oxides of the nonmetals in the upper right-hand corner of the periodic table, including these guys are also gases, as well as our noble gases. So how do these guys move around? Well, gas consists of small particles that move rapidly in straight lines. So I kind of think of them as little like fruit flies or gnats where they buzz around, right? So they move really, really, really fast. And they essentially have no attractive or repulsive forces. They're very far apart and they have very small volumes compared to the volume of the container that they occupy. And they also have kinetic energies that increase with the increase in temperature. So as we get warmer, they're going to buzz around even faster. So you can kind of think of these also as like when you're playing Quidditch, right, for Harry Potter, the little gold guy that you're always trying to catch, right? They just kind of buzz around. So what are different properties that are going to describe the gases? Well, they're described in terms of 4 properties: pressure, volume, temperature, and amount. And these are, so pressure is P, volume is V, temperature is T, amount is N. The way you can remember that is like, remember in statistics, N equals 5, sample size equals 5, so the number or amount would be the N, right? And so the pressure is the force that's exerted by the gas against the walls of the container, and it can be measured in atmospheres, millimeters of mercury, torr, or pascals. Where the volumes is the space that's occupied by the gas. It's measured in liters or milliliters. The temperature is the determining factor of the kinetic energy and the rate of the motion of the gas particles. So again, the warmer it is, the faster they're going to move. This is measured in degrees Celsius, Kelvin, and this is required for calculations. And again, the amount is N, and that would be the quantity of gas present in the container. That would be grams or moles, and the N is, again, also going to be required for our calculations. So the volume of a gas, this is the same as the volume of the container that it occupies. So it's usually measured in liters or milliliters, and it increases with the increase in temperature at a constant pressure. So again, the gas particles you can see here are moving in straight lines within the container, and the gas particles are going to exert pressures when they collide against the walls of the container. And we get to actually play with some calculations and see how those are going to be affected by different volumes and temperatures, etc. Temperature is going to be the temperature of a gas and how it relates to the average kinetic energy of the molecules, and that again is measured in kelvins, and Kelvin is a temperature scale. So degrees Celsius plus 273 equals the amount of Kelvin. So when the temperature of a gas is decreased, so think of them, they kind of slow down like molasses on a cold winter day, and so they have fewer collisions. Okay, so they're actually going to be smaller. Where when it's increased and raised in temperature, then the molecules are going to get like super excited and they're going to have even more collisions. The pressure is a measure of the gas particle collisions with the side of the container. Then it's measured in units of millimeters mercury or torr. Also, it could be measured in atmospheres or pascals, kilopascals, or pounds per square inch. The gas particles in the air exert pressure on us, and that's called atmospheric pressure. So you can see here we have the atmosphere pushing down us so that I don't float around in the lovely sky. Barometers is also a measure of pressure. So a barometer is specialized and it measures the pressure exerted on the gas by the atmosphere. So sometimes you hear of barometric pressure. So, I think you can go on the weather app and it'll actually tell you these. And so this is measuring the pressure that's exerted by the gases in the atmosphere. And this indicates the atmospheric pressure as the height in millimeters of mercury in the column. So here's a standard version calculation. So 760 millimeters of mercury is equated to 1 atmospheric pressure, or 760 torr. So how this is measured is the barometer here, and it was invented by this lovely scientist. And so exactly at 1 atmosphere, the barometer tube is exactly 760 millimeters high, and they use mercury to measure it. So that's why some thermometers still actually use millimeters of mercury. Thermometers, that would be temperature. They still use mercury. It's a great transducer. Anyway, atmospheric pressure is the pressure exerted by the column of air from the top of the atmosphere to the surface of the Earth, and it decreases as altitude increases. So 1 atmospheric pressure equivalent is met at sea level. So you can see at sea level we're going to have a P of 1 atm, where when we're higher up in the mountains we're going to have like a P of 0.7. So here's your lovely summary chart for the units of measuring the pressure. So keep that handy for when we do some of these calculations. So atmospheric pressure changes, again, with different variations in the weather as well as altitude. Coming into summer right now as I'm recording these, on a hot sunny day, the mercury column rises, which indicates a higher atmospheric pressure, where on a rainy day, the atmospheric pressure falls, and this causes the mercury in that column, therefore, to fall. So here's a couple different locations. The Dead Sea altitude is negative 0.4 kilometers, where the atmospheric pressure is going to be 800. Where when we're looking at LA or Denver, you can see that these different the volumes and pressures are going to change. So let's do a little study check. So pause me and let's figure out what these guys are. All right, for question 1, did you get 0.625 atmospheres? So the question was, what is 475 millimeters of mercury expressed in the atmosphere? So again, the answer is going to be 0.625 by taking 475, using this calculation to derive to 0.625. All right, for question number 2, the pressure of a tire is 2 atm. What is the pressure in millimeters of mercury? Well, again, the answer is going to be B by doing these calculations. All right, great job, you guys. Let's do another one. All right, pause me and come back. All right, so for the answers, the downward pressure of millimeters of mercury, right, and a barometer is what? And it is the same as the pressure of the atmosphere. Okay, it's not millimeters of mercury, it's just on mercury. And for question 2, the water barometer is 13.6 times taller than the mercury barometer, because, and your answer was, water is less dense than mercury. Right, great job, guys.